All right, so great to have you all here. It's 2 p.m. from where I'm talking. I'm currently in Rome at the moment, and it's 10 p.m. in Melbourne. Thanks all of you all around the world to be able to attend this session. This in particular is the second session of BPMDS Session 2, Enhancing the Value of Data in Process Improvement. This is Claudio speaking from Sapienza University of Rome. First and foremost, let me thank Laura for the incredible support she's given to us this far, and to all the University of Melbourne for their huge, impressive efforts and help they've given us thus far. So, as in the usual, best tradition of a working conference, such as the working conference of business process modeling, development, and support, BPMDS for France, this is an event which is meant to be highly interactive. So we are in the online setting. Let's keep on with this tradition. I recall you all that currently the panelists can take the parole anytime. If you want to ask any questions, feel free to use the Q&A button. You can see it down there at the bottom of your screen, or actually of your Zoom window. The chat as well is fine as well. If you want to ask live, of course, you can raise your hand. You can see there is a little icon there again in the bottom bar. And once the talk is over, we can give you the token, so to speak. All right, so enough from the presentation. I'd say at this stage we can switch to the first presenter. It's Mr. Yang Lu from the University of Sydney, with his and his co-authors paper, Detecting and Understanding Branching Frequency Changes in Process Models. I give the word to you. Thanks a lot.
Thanks very much. So just before I start, can you confirm if my voice is okay?
All right, and we'll also see your slides.
Thank you so much. Hello, everyone. So my name is Yang Lu. I'm a PhD candidate from the University of Sydney. Today, I'm going to present our paper, which is Detecting and Understanding Branching Frequency Changes in Process Models. Process drift is now a well-defined topic in the field of process mining, which often refers to a time point when there is a significant change among process behaviors. Normally, process drifts are related to changes of control flow structures. So in the first picture, we show an example control flow structure change. As you can see, at time t, one of the branches of the process model disappears, and activity A and activity B will no longer execute after the process drift time t. However, the branching frequency changes are different. For branching frequency changes, the control flow structure of the process remain unchanged, but the execution probabilities among different branches can change. As shown in the second picture, for an example, before the change, the frequency of choosing activity A and activity C after activity S are equal, but after the change at time t, the frequency of choosing activity C is much higher than the frequency of the chance of choosing activity A after activity S. The branching frequency changes can be seen as a special case for process drifts. So in the paper we write, we focus on two problems. One is to detect changes of frequencies between different options when there is an exclusive choice in the process model. Specifically, in our study, we focus on the changes in Petri nets. And we also aim at providing a comprehensive report of our detected changes. So there are several challenges related to this issue. So firstly, for the real-life event logs, we can get different models when using different process discovery algorithms. As a result, so assuming you only have an event log and you do not have a process model, and you want to understand how the branching, the frequency changes between different branches, but if you use different, let's say if you use different process discovery algorithms, you might end up with different branches. So in that case, if you want to understand the frequency changes between different execution branches, it can be difficult. Secondly, even if the process control flow structure remains unchanged, we can still get different process model because the process discovery algorithms have different ways to handle the infrequent behaviors. We show an example in the picture. So assume we have a process drift point at time t, which is branching frequency change. We put the event log as an input into a traditional, maybe a statistical based process drift detection algorithm, and assume we detect the process change point at time t. Then in order to find out what is happening, a common way is to split the original event log before and after t. Then we will get two sublogs. After that, we can bring the two sublogs into the current process discovery algorithm. But because the process discovery algorithms normally have their own ways to handle the infrequent behaviors, so even if the process change is only related to branching frequency changes and the control flow structure remain unchanged, but we can still get different process models in some cases. So in such a case, we will mistakenly treat the process drift as a structure change instead of branching frequency changes. Lastly, most current process discovery algorithms only return non-stochastic process models. So they only tell the possible behaviors, but they do not tell their own each probabilities. So in conclusion, we believe it is not feasible to understand the branching frequency changes if we do not have a process model. So in our design method, the input of our method are a Petri net and event log of that model. The process model can be either automatically discovered by an existing process discovery algorithm, or it can also be drawn by process experts or domain experts. So in Petri nets, an exclusive choice split is often caused by a place with more than one outgoing arcs. If users are interested in frequency changes in one or multiple exclusive choices, they can select such places and only focus on process drifts on the place they select. Otherwise, all places with more than one outgoing arcs can be selected as the interesting place. Then we do some model trace alignment. Through that, we can discover which option has been selected each time a decision needs to be made. We then list all the decisions as a choice sequence and identify points based on the choice sequence we constructed from the model trace alignment. Finally, our method will be able to generate a comprehensive report about the detected change points. I will provide you with more details in the next slide. So in this slide, we show an example event log and process model and how we construct the choice sequence based on the event log and process model. So firstly, we have a Petri net and we have an event log. We first select the place P as the interesting place where we are studying the branching frequency changes between activity A and activity C after activity S has been executed. So for your convenience, we have marked the interesting place we select in red color in this slide. Firstly, we label each possible option by an integer after the decision point. In this case, we label the first branch as 1 and the second branch as 2. Then for each place, we find its incoming and outgoing transitions and perform a model log alignment. After this, we look at the model moves obtained from the alignment. So in the two example here, in the first example for the trace SDAB, after the alignment, because we observe the transition T2 in the model move, so we can conclude a decision has been made and T2 has been selected in this round. And in the second example, it's the same, but we observe transition T4 in the model move sequence. So we can also conclude a decision has been made and T4 is selected for this decision. So as a result, for the first trace, we will add 1 in our choice sequence. And for the second trace, we will add 2 in our choice sequence. Besides, each element in the choice sequence will also have a timestamp. The timestamp can be the timestamp of the nearest log move. For example, in the first example, the timestamp of the new added element in the choice sequence might be the timestamp of S in the trace or timestamp of A in the trace. And in the second example, the timestamp of the added 2 in the choice sequence, we can take the timestamp of activity E or activity C for the new added element. It is worth mentioning that in this stage, we use the ID of each transition instead of activity names when determining which option has been selected. For example, instead of looking at the activity name SAC in the model move, we look at the ID of each transition. We look at T1, T2, and T4. In this case, we will be able to handle the invisible transitions and duplicate tasks correctly. So after we have constructed the initial choice sequence based on the model trace alignment, we will get a choice sequence, but the choice sequence may not be ordered correctly by their corresponding timestamps. So we then we then sort the initial choice sequence we got from last stage to make sure they are ordered by their corresponding timestamp. So after we sort the choice sequence, then for the place we selected, we will have a stream of decisions which are ordered by the time when each decision is made. So after we constructed the choice sequences, the problem of finding branching frequency changes of the exclusive choice structures we select is then changed into identifying a change point on sequences of categorical variables. We can then apply some existing change point detection algorithm to find change points. In this specific implementation, we use an external library called Raptors, which is a Python-based library containing various change point detection algorithms and has also been used in some other process drift research. Finally, based on the change point we detect, we can generate a comprehensive report by simply calculating the frequency of each option between change points. As an example here, if we detect a change point at time t on the choice sequence of the place P, we know the process drift is related to the choice between activity A and activity C after activity S. As a result, by calculating the frequency of 1 and 2 in the generated choice sequence between before and after time t, we will be able to generate a comprehensive report about how the branching frequencies are changed between A and C after activity S. For the evaluation, in order to prove the validity of our method, we use a publicly available log, which is the Italian help desk log. It describes a ticketing management process of the help desk of an Italian software company. Although we do not know the exact ground truth about process drifts in the event log, another study about process drifts is found, and it also uses the same log to analyze the drifts inside the log. So we hope we can verify the validity of our method by comparing our results with the reference paper. So firstly, we quoted the process model directly from the reference paper, and we focus on the place marking in red in the slide. Then for the 3 options, we give each option a unique label. So in this case, we give the activity weight label 1 and the invisible transition label 2 and the required upgrade activity label 3. So then we follow the steps we described in the previous section. We put the discovered choice sequence into an external library to detect change points, and then we finally generate a report of our results. So based on this log, we identified two branching frequency changes in this event log for our selected exclusive choice structure. One is in the August of 2012, and another is in the April of 2013. A comprehensive result is presented on the slide. Before the first drift point, the frequency of choosing required upgrade after take-in charge ticket is quite low, and the frequency of choosing the invisible task is much higher than the frequency of choosing wait. Between the two drift points, the frequency of choosing required upgrade is much higher than before, and the frequency of wait and choosing the invisible task are almost identical, which are around 45%. After the last drift point, the frequency of choosing required upgrade almost remains unchanged, but the frequency of choosing activity wait becomes much higher than the frequency for choosing the invisible task. The first drift point is also reported in the reference paper, but for the second drift point, since the frequency change between the activity wait and skipping to and the hidden transition is significant, which is around 20%. We believe the second drift point we find should be correct. In conclusion, so in this small project, we proposed a model-based method to detect and understand the branching frequency changes in process models. So with our method, we can easily produce accurate and comprehensive results about branching frequency changes in process models. And our method will be able to handle the invisible and duplicate tasks in the Petri net. However, there are still some limitations and potential future work of this project. The first thing is, so the way to label the branches could potentially cause biases. So we aim at trying different ways to identify the drift points based on the choice sequence in the future. Secondly, so the current approach is unable to characterize the drifts. For example, we cannot tell if that drift is a sudden drift, or it's a gradual drift, or it's an incremental drift. Lastly, the detection results may not be accurate if the event log is not conformed with the process model. Okay, thank you very much.
Thank you, thank you. So, well in advance with the schedule. Well, I've ever heard anyone complaining about, getting less time than was supposed. So thanks very much for your synthesis skills. Very interesting talk, also very nice paper. I would recommend everyone to go and download the proceedings of BPMDS, which are already available online, and also have a second look at the papers that are being presented during this session. Also technically very interesting to be read. So thanks a lot.
Thank you so much.
Let's see. Let's see. So are there questions from the attendees? I don't see raised hands yet. So I would warmly recommend everyone to, okay. So Nina, here you go. Let's enable you.
Now I'm not muted and you can hear me, right?
Yes, we can. Thank you.
Okay. So I have, first of all, very nice talk, and I have two questions. One, I think you considered about how you rely on alignment as a first step. And as you know, that each trace can be aligned different ways. So I think this is a bit problematic, and how can you handle it? This is one question, and perhaps you can make some experiments and test different alignment techniques to see to what extent the result depends on the alignment. So this is one point. And the other is, I'm not sure I understand how you really establish the date, an exact date of the drift, because if you take it a bit forward or backwards, then you may get different distributions. So that's the question.
Thank you so much. So I think I want to answer your second question first. So So basically, when we are constructing the choice sequence, each time a decision has been made, we put a new label into the choice sequence. But each choice sequence also has a corresponding timestamp, and the timestamp and how we get the timestamp really depends. So it can be the nearest log move to the model move. So let's say, for example, in the first trace, after we find the transition T2, we can use because actually this move is a synchronized move, we can use the timestamp of activity A in the trace for it, but we can also take the timestamp of S. So one is before the decision, one is after the decision. So I think this is more like a user-defined parameter. So how you want to choose the timestamp, and then we put both the choice and the timestamp into the choice sequence. After that we sort the choice sequence again, and when we are detecting the change point, we only use the number, so 1, 1, 2, 1, 2 to detect the change point. Let's say if we find the change point at 2 in the choice sequence, but 2 also still has a corresponding timestamp, so we can take the timestamp of 2 as the process drift time.
Okay, you can still, I mean, you can still move it forward and backward and get different distributions, but you need to settle for one point. So I understand what you're saying.
Yeah, so because we sort the timestamp from the beginning to the end, from early to late. So, but I am not 100% sure, but I guess if you detect the process drift point from backwards, you should get the same results probably. I think depending on what techniques you are using to find that drift point in the sequence.
Perhaps you can also experiment with this.
Yeah, that's a very good point. Also, I think there might be some other ways to detect the change point. For example, we might be able to put a moving window on the choice sequence and say if we can find, maybe use some statistical method to say if a process drift point can be reported when we find a significant change just on the choice sequence. I think there are different ways. I think also for your first question is, yes, so this method, we rely on the alignment to find out which decision has been made. The main reason is we want to handle the invisible transitions and duplicate tasks, especially invisible transitions. So if
it's clear why you need that. I mean, you obviously need that. I don't doubt it.
Yeah. So unless the event log is 100% conform with the model, we will need model trace alignment to determine which decision has been made. But yeah, I think if the fitness is not high enough, we might encounter some problems.
So perhaps you may also experiment with different alignment techniques and see to what extent your result depends on the alignment, I suggest.
Thank you so much for the input. Thanks.
Very good. So indeed, in the very spirit of a working conference, we have a nice discussion about even potential future endeavors. That's great. So I see already there is another hand being raised, but first I would if you don't mind, Edwin, read out loud a question in the Q&A frame. So Edwin Hemala asks us if by drift, are you referring to the deviation from standard processes or exceptions?
I think this is always a problem. So the way I say this is, so for a process drift, if let's say you have at time t, you have a behavior which does not exist in the previous log before the process drift point you detect, it can be a drift, but it might also be an outlier or noise. I think, so I believe the way, so how we differentiate a noise and real process drift, it depends on the techniques you select to, find the drift point on the choice sequence in this specific case. Because in this experiment, we used the rupture. So I think that is it's a change point detection method based on the signal. So it's for detecting signal changes. I think about your question for this part, I think we need to do more experiment to find it out, because we didn't do it because this is a short paper, so we haven't done experiment on artificial logs with noises. Yeah, but I think it's a very good point. So it's always like this. So if it's we find a new behavior, if it's a drift point or if it's a noise.
Yeah, right. I hope Edwin was also satisfied with the answer. If I may add a little bit today, it's also interesting to see how this recurring issue comes over and over again from the data mining field, right? So you don't know if rare events are actually an error or something which is like an exception we should take care of. So yeah, great. So yeah, fantastic to see there is already a plan for this sort of experiments. Now we have a question from, sorry for mispronouncing your name in case, Yunnan Park. So maybe you may want to, unmute your microphone and ask live.
Yeah, thanks. Yeah, my name is Yunnan Park. Yeah, thanks for your inspiring talk, and it was really good. And which also means that I have several questions, but I try to get into the point immediately. So my one of the essential questions that I have is about your design choice in terms of using the whole process model instead of the part of Petri net construct. So for example, if you want to focus on exclusive choice, and then you assume that all the behaviors in the event log is conforming to the process model that you have, I also would expect if you use the exclusive choice construct instead of the whole model, and then projecting your event log onto such activities existing in the exclusive construct, Petri net construct would also work, but probably there would be some reasoning behind your design choice. So that would be my question.
So what do you mean by exclusive choice structure? So you mean we only need to look at the input transition, output transition, and the place, or?
So by exclusive choice construct, I mean yeah, it's quite hard to explain without any figure. But for example, in this slide, I can say that the transition S and then place P and then transition labeled with AC would be an example of exclusive Petri net construct. And then there, what I can imagine is you can also use that construct, that part of the Petri net, instead of using the whole Petri net to calculate alignment. If you assume that the behaviors in the event log are all conforming to the process model.
Oh, I haven't thought about that before, but I think it sounds like a very good idea, I think. Because in this way, we might reduce some biases caused by the model trace alignment, I guess.
Yeah, so probably to consider some non-fitting behaviors, I think it would be helpful to have, let's say, the whole process model, but probably that's the reasoning behind them.
Yeah, thank you very much.
Yeah, thanks for your answer and nice talk.
Thank you so much.
Very good. So I don't see any further questions from the audience. I'd like to ask something, but let's keep this offline for the interest of time. And thank you very much for your presentation. That was very interesting, Yang Lu. Also, as we can see from the plethora of questions that sprung from it. Thank you very much. And right, so I now leave the stage to Yael Dubinsky from the University of Haifa. It's 3:30 p.m. there. So it's another detection paper, but in this case, it's detecting the split cases workaround in event logs. Looking forward to your presentation. Please go ahead, Yael.
Tell me, guys, if you all can see my screen correctly. Can you guys see the screen?
Yes, we can.
Great. Okay. So hi everyone, I'm Yael, and today I'll be talking about detecting the split cases workaround in event logs done by me and Nina. So let's start with an example. Meet Bob. Bob is a purchasing agent working in a large company, and as you can see, he's pretty upset. Very urgent and purchase request landed on his table. An important customer of the company wishes to make a very large order, and if the company cannot fulfill the request on time, the important customer will replace the company with another supplier. So as Bob is already familiar with the handling process of purchase requests, he knows that requests this big require a whole approval workflow involving many managers and supervisor approvals. These approvals often take a long time as the approval repeatability patch. So this means that the approval workflow will slow the whole process down and the customer will not be happy about it. So this is when Bob decides he needs to do something in order to promote the handling of the urgent request. He decides to open 2 purchase requests instead of just 1, each with half of the original amounts and quantities. Bob is aware that the request with half of the amount does not require a TDS approval workflow and will be executed a lot faster. So the 2 requests are executed, the approval workflow is indeed avoided, and the requests are completed way ahead of the deadline. So everybody is happy. All of the originally requested items arrive quickly to the requester, but is really everybody happy? It seems that all is good. Even though 2 process instances were executed instead of 1, the final outcome is the same as if Bob would have created only 1 purchase request. But remember that the whole approval workflow was skipped. Bob wanted to avoid the approvals in order to quicken the process and benefit the company, but the approvals are there for a reason. The process steps being bypassed by this workaround are likely to be crucial for valid process execution, minimizing business risks, and for complying with regulations and legislation. So this example demonstrates a very common behavior, which we refer to as the split cases workaround. This workaround was identified as one of 6 most common workarounds in business processes in a qualitative exploratory study. So in a single sentence, we can say that this workaround is splitting one process instance into several ones, so that each instance separately is eligible to an easier, more preferable path than the original one. The split cases workaround mostly occurs in processes with complex workflow containing many decision rules that are enforced by the system, or particularly decision rules which lead to approvals and tasks that are tedious and slow down the process. So in this workaround, the process participants are aware of the rules and the activities they lead to, and they may aim to avoid certain tasks or approvals which should be triggered by these conditions. So why does it happen? What causes employees to perform this workaround even though they know it deviates from the planned process model? This behavior is often performed with good intentions. Employees who wishes to quickly advance the process in urgent cases in order to do their job the best way they can. Employees may also perceive the decision rules and the conditions as restrictions which form obstacles from a proper job execution. This may also imply that there might be a problem with the process model itself. But in other cases, this workaround might be performed for negative reasons. For example, it has been revealed in 2018 that Nigerian military Qifan companies were involved in a vast procurement fraud, which included splitting procurement contracts and concealing benefits and incentives given to the supplier. Another common example is money laundering, splitting one financial transaction into several smaller ones in order to evade special taxes and fees. So is detection possible? From the examples I've just described, we understand that it is important to be able to detect this data. Despite its importance, the existing conformance checking techniques are not geared to detect it. Up until now, the techniques focused mainly on examining intra-case behaviors, which are examination of each case in the event log separately. But this does not fit, as the behavior depends on the relationship between multiple cases. And furthermore, each case by itself must be fairly conformant and does not deviate from the model at all. So in order to detect this behavior, it is required to establish the connection among the cases concerning the control flow, the data values, the involved resources, and the time period. So what's our goal in this research? We aim to understand, define, and characterize the split cases behavior, and we first aim to understand what properties this behavior has from the business process point of view. As we've seen before, this behavior is all about the connection among the cases. So we're trying to understand its properties regarding the control flow, data, resource, and time period. After we understand and define the properties, we can formalize the behavior. We rely on a Petri net with data notion, which helps us to define the relationship between different paths in the process model. So as the split cases behavior may occur only under certain circumstances, we also define several assumptions, which rely on this Petri net with data as well. After the formalization, we suggest an approach to detection in event logs. We evaluate our approach with both simulated and real-life logs. So in our formalization, we rely on a Petri net with data. So let's first have a quick look on its components. First, we have a regular Petri net, which consists of a set, transition, and flow. The second thing we have is the data items of the process. We also have read and write functions, which label each transaction with the set of data items it must read and write. And last but not least, we have a guard function that associates a guard with each transaction in the form of a predicate of some data item. So this Petri net with data we see below represents a part of the motivating example. The create activity writes the amount data item, and then the transition that leads the approval workflow has a guard over the same data item. If the amount is greater than 100K, the transition is triggered and the approval workflow starts. Otherwise, the process skips the approval. So as I said before, this behavior may occur only under certain circumstances. So we form several assumptions for this behavior to be plausible at all. The purpose of the assumptions is to characterize the preferable path in the process model. As you see in the example, the employee was aware that there are two options. Either the process goes for a co-communicated approval workflow or the approvals are skipped. So the employee prefers to skip the approvals in order to shorten the process. So our goal here is to show the split cases behavior is possible when such preferences will take place. So the first assumption says that there exists a value function v, which assigns a partial order relation to traces. So it can be said that the value of some trace A is greater than the value of another trace B. So this value function is not necessarily explicit or even known, but it marks that an employee may favor one path over another. Considerations may relate to various things, such as time, effort, or even personal relations with other employees. Second assumption says that there exists data items such that different guarding conditions over this data item lead to different traces. Like in the example we saw earlier, the data item was the amount. If the amount is greater than 100K, approval is needed. Otherwise, the process continues without approval. The third assumption combines the first two. So we consider two traces that satisfy the second assumption, meaning each of the traces has different guard function over the same data item. For these two traces, we assume that the value function v of the first trace is different than the v of the second trace. In other words, the value of a data item may determine whether a path is preferable or not. And the existence of these three assumptions may motivate the creation of split cases. The typical scenario here is when a value of a data item can lead to an undesirable path for a guard condition associated with the same path. And to avoid it and improve the value function v, an employee might decide to create several split cases, each having a data item value that ensures a preferable path. And the total sum of the data items over the split cases should be equal to the original one. So after we have these three assumptions, we can define what is a concealed case and what are split cases. The concealed case is the original case that was not created. It is an assumed case whose trace does not appear in the log. Instead of this case, the log includes traces of at least 2 split cases. Then, given the above, we can say that the value function of the concealed case is less than the value function of each of the split cases separately. So now we have a definition of the split cases behavior. And as I said earlier, our goal here was not only to define this behavior, but also to suggest a detection approach in event logs. And in order to do so, we infer some properties of the split cases behavior as they would be reflected in a log. So the first thing we find is that this behavior can be observed in processes in which there's a data item D, which affects some process properties. As in the example we saw earlier, it can affect the control flow through a decision rule that depends on the value of this data item. The second property is that the process participant, for example, an employee who creates the cases, is able to perceive a value function V for different possible traces and prefer one trace over another. The third property is that split cases are created by a single process participant and in time proximity to one another. And the fourth property is that split cases are similar to one another in some of their data values in correspondence to the concealed case that was not created. In other words, this means that the concealed case has a data value that will be kept while creating the split cases. Most of the time, this data value somehow connects the case to some entity. It can be the supplier from which the order is made, customer who ordered the items, the shipping date, etc., etc. The splitting cases will all have the same value in this data item, as they all should be connected to the same entity as the original case. So based on the properties we just discussed, we can define the behavior and propose a detection method. So first, let's look at the inputs of the method and then the algorithm itself. The method requires 3 inputs, and the value of these inputs can be defined by using existing process mining techniques or by consulting with the process owner. First, we need to know the data item on which the decision rule in the process depends. This is the data item which is going to be split in order to create the split cases. For example, the amount of the purchase request. Second, we need to know the threshold condition over this data item. We need to identify a decision rule in the form of a predicate in this data item, such that a threshold value determines the process path to be selected. And note that we expect different possible paths to have different value function values. For example, if total amount is greater than 100K and approval is required, and in this situation, 100K is the threshold value of this data item, as the path that goes through this approval is less preferable than a path that skips it. The third input we need is the uniting attribute. As we discussed before, we expect the split cases to share some of their data values, which the concealed case would also have. So, for example, the customer, the due date, the product, as we talked earlier. So now let's look at the algorithm. The algorithm uses a moving time frame with 2 parameters, the time frame size and the iteration size. The time frame size is the time window in which the split cases are created, and the iteration size is how much we move the time frame each iteration. So the idea here is to identify suspects for this split cases behavior. The suspect cases are all going through a preferable path created within the same time frame and by the same resource, and all have the same uniting attribute. So first, we filter the log and leave only cases which have data item value which is below the threshold, meaning they have a preferable path. Then we can start looking through the filtered log with a moving time frame, and we create sets of suspects. In the last step, we calculate the sum of the data item over each set. So this data item value is the value the concealed case would have. So if the sum of a set exceeds the threshold, we can say that the cases in this set are possibly split. So how did we evaluate this detection approach? First, we used simulated logs. We created 9 logs, all representing the same process of order handling and containing concepts of the split cases behavior. We created logs with both normal process behavior and logs with irregular behavior. The regular behaviors we chose are account executives and peak work days. Account executive opens many cases for the same customer, and peak work days, there are many cases that are created in a short period of time. So these irregular behaviors are supposed to make it harder for the algorithm to detect real split cases. So the evaluation with the simulated logs is important to us as they form a non-ground truth. We use these ground truths to produce quantitative evaluation of this approach in the form of precision and recall. We want to demonstrate the success rates of our approach, but however, simulated logs are not enough by themselves, as real-life logs are much larger in size and are more complex than the simulated ones. So, and they also contain more unpredictable behavior. So therefore, we use both simulated and real-life logs in our evaluation. So the goal of this experiment with the simulated logs is to assess the dependency of the results on the input parameters. Therefore, we change the value of the parameters over the experiment and search for the value that lead to the best precision and recall. So these are the results of the experiment. The numbers under the time frame size and iteration size are multiplied by the mean time between cases. And the mean time between cases here was about half an hour. So for example, the first line represents a time frame size of 3 minutes. So in the first phase, we kept a constant ratio between the time frame size and iteration size, and we got a maximal value of F1 for a time frame size of 0.5. In the second phase, we examined different iteration size with a fixed time frame, which was the optimal time frame we got in the last phase. So here we get a maximal F1 score for iteration size of 0.1. So in order to evaluate with the real-life log, we use the BPI challenge of 2019 log. This log represents a purchase order handling process. The possible decision rule here was indicated by the challenge report and also was confirmed by us based on the data. The possible decision rule is that cases with cumulative net worth over 100K take much longer than cases below the sum. So cases over 100K have mean duration of 100 days, and cases below the sum have mean duration of only 70 days. So this might be the basis of a possible decision rule. The uniting attribute here was decided by the domain knowledge provided by the challenge, which determined that each purchase order is linked to a vendor. So the vendors are the uniting attributes here. We test this log with the optimal values we got from the simulated log evaluation, which are time frame of 0.5 multiplied by the mean time between cases and iteration of 0.1 multiplied by the mean time between cases. In the table here, we can see an example for cases the method determined the split. They are all created by the same user and linked to the same vendor in a time period of only 15 minutes. The cumulative net worth here is 37K in average. So this means that the possible concealed case would have indeed exceeded 100K euros, which is our threshold. And please note that this is a real-life log. We don't know the ground truth here and that there are split cases behavior at all in this log. So we can't say for sure that these cases are indeed split, but we can say that our detection approach is applicable to a large event logs and yield results. So in conclusion, the split cases behavior is commonly observed in practice and might sometimes bear harmful consequences. And although its importance for detection of such behavior is recognized, existing process mining techniques are not geared to accomplish this task. In this work, we formalized the behavior and suggested an approach for detecting it in event logs. We evaluated the detection method using both simulated and real-life logs, and the experiments with the simulated logs assess the dependency of the results on the input parameter, and the experiment with the real-life log demonstrated the applicability of our approach. Some future research can investigate more complicated scenarios and test the approach in a real organization where suspected split cases can be further investigated. And that's it. Thank you very much for listening. Q&A time.
Thank you for your great presentation indeed, Yael. And as you write right here, Q&A time. So I will invite warmly all the participants to raise their hand or type their questions directly in the Q&A spot as you wish, or also the chat. Everything is fine from us. All right, so well, while you type in or you look for the button to click to raise the hand, I would start by first with a comment. So it's a very interesting topic, I'd say. Also in terms of cybersecurity, that could be great with large margins for applicability. That's very good. Thanks for bringing this topic up. I wanted to ask, well, a couple things. So first, I wonder if you had considered perhaps integrating, for future research, process query languages so as to pre-filter the event logs with certain characteristics you have already made explicit in your assumptions. So first, or if it's like currently completely algorithmic, so it's something that you don't aim at making customizable. I don't know, like it is. Of course, I leave room to you. And another thing I would like to ask, if you could please elaborate a bit more on the reason why we not only need a uniting attribute to detect that it's actually the same, the same case being split at some stage for who knows which reasons, but also that it's the same resource. So I wonder, because usually resources tend to take, I don't know, 1-2 tasks, not more, but then there could be differentiation of resources along the workflow. So
yeah, you're right. So the resource we assume is the same over the all split cases, because we assume this is the resource who initiates the split cases at all. He's the one who decides, okay, I need to split the cases now. So he's the one who creates the cases. Of course, he's the resource only in the first activity of the process, not over all of the activities. And the previous question was about the filtering, right?
Yes, right.
So we actually do the filtering in the phase of the, in the phase of the looping the time frame, we do the exactly same filtering as in the properties we defined. We filter as only the same resource creates the case, the same attribute, the same uniting attribute.
Understood. Yeah, right. So I was wondering if you were using a special language for this, or is it like in?
No, actually not. Actually I did it in Python. It's not a special language at all. Just just filter the data frame, not something special.
Sure. Well, okay. Well, room for future parts. That's good. So
yeah.
Thanks a lot.
Yeah.
All right. So we have again. Oh, sorry. I said. So thanks a lot. And we have again Yunnan Park from the audience asking questions. So I would say, if you could please unmute yourself, or at least your system, and
yeah,
feel free to proceed.
Can you hear me?
Yes, we can.
Yeah, thanks a lot for your talk. And I have a minor question about your evaluation part. So in the real life evaluation, you use the. Can you go to the slide so that I can have some reminder myself? Yeah. So you use BPI Challenge 2019, and here my question is about the value function. So how did you implement the value function here to assign the partial order relation? Was it by using the timestamp information?
So yeah, we use the timestamp information in order to to detect the first activity. But of course, we didn't know that there was a value function here because it's a real life log. We only saw that there's a decision rule that may motivate some employees to commit this workaround, because cases over 100K really take much longer than the cases below the count. But of course, we have no information about it.
Okay, so if you try to connect your assumptions about partial orders in this real life example, can you say something relevant here in this BPI Challenge 2019 event log?
Well, we can see that the cases that the detection method detects the split are indeed they need have much less duration than other cases. For example, the 3 cases below, they all have duration between 70 and 80 days, if I recall correctly.
Yes, yeah. Thanks a lot.
All right, so thank you very much. So I think, well, if there are any further questions from the audience, I would then thank Yael again very much for her presentation and the brilliant theme she exposed. Thank you also for the co-author. Thank you to the co-author. And all right, so although we are slightly in advance with our schedule, I would proceed with the next paper. So it's Felix Holz from the University of Rostock. Are you there, Felix?
Yes, I'm there. You can hear me?
Okay, great. Yes, perfectly. We can also see you and hear you clear and loud. Okay, so Felix will present a paper about towards a content-based process mining approach in personal services. Very intriguing. So, Felix, the stage is yours.
Yeah, thank you very much for the introduction. I share my screen. And you should see the slides, yeah?
Yes, we can. Thank you.
Okay, perfect. So, thank you for the introduction. I'm Felix Holz from the University of Rostock, the chair of business information systems. Welcome to my presentation of my paper with the title Towards a Content-Based Process Mining Approach in Personal Service. What do we have planned today? See the agenda first. I will introduce the topic with a little motivation, then giving a brief overview about the theoretical background with a focus on topic modeling. The core of our work is the approach and the case study we conducted. So we made some interviews, we made a prototype for topic modeling and created models in a real world social service enterprise. So naturally we evaluated the results a bit. So at the end, I will conclude it. The motivation. So we want to create solutions for the domain of personal services. Personal services are directed at enhancing the mind or the body of a client. In most cases, it's a long-term process to achieve the goals of the client. Especially in our case, we want to create support solutions for social service providers. For example, they handle juvenile drug addiction problems, or they support disabled persons in assisted living for participate more in the society. And in this domain, traditional analysis methods have some issues, since it's a very flexible and unstructured environment. Every case has a bit of an individual touch, so it's not that easy to conduct some process mining techniques. So we have applied them in the past, but the resulting model couldn't give that much of insights. So a big issue in personal service is the limited set of activities. And on top, the activities are more general formulated. So to give an example, from activities like a telephone call or consultation appointment, you can't read much out of them in a model. So the thing is, the thought is, the activities have to be enriched. Luckily, in social services, the employees have to write reports due to law. So these are unstructured data, and it's a resource that is commonly unused, I will say. So our goal is to enhance the process mining or the process model with the content written in these reports. So and replace the general activities with the content of the reports. So that in the end, that the model shows which contents were handled and how the relations between certain contents are. Therefore, we created an approach to apply a topic modeling method to structure the text before the process mining step, and tested and evaluated it in the social service enterprise. So that wraps up the motivation. We come to the theoretical background. Since process mining is a common and known concept, I will skip it and focus more on the topic modeling part. We do see here in this figure the most general topic modeling technique. It's latent directly allocation. So in general, the topic modeling is a way of systemizing underlying text into their topic portions. So we see here in the figure, we have a document in the middle, and this is containing a bunch of words. Words are the defining entities for determining topics. So, and you can see in the left the topics defined by words that appear in the text. So you see the yellow one, it's about genetics. So we have the words like gene, DNA. On the right-hand side, you can see the topic proportions. In other words, let's say which topics occur in the document and with which amounts. We see here in the example, the yellow topic is has the makes the largest part of the text. So LDA is a bag of words approach, which utilizes probability distributions and random drawings from them. So if you apply it in reality, it's somewhat random, and the topics are undirected, to say less. So while LDA works completely unsupervised, meaning the computed topics can lack a meaningful direction. So to cover this issue, we add some supervision to that with the labeled LDA technique. So we see in the slides, the difference is that we have an annotated data set with labels applied to the documents. You see in the figure at the bottom, the documents have the labels on the left side, and LDA learns for each label a word distribution, meaning words which are most relevant for the topic, respectively the label, the word distributions we see bottom right. These distributions can be used to classify not annotated documents, and the labels itself can be seen as representative of the text's content. So this example is a bit wonky, but I guess you get the gist of it. The advantage of labeled LDA is to include expert knowledge for more directed way of structuring the text. So we need some annotated data sets to conduct LDA in a successful manner. So we need train data for the word distributions for the custom labels, and therefore we designed an approach to cover that. Roughly, there are 3 steps given. It's a lot of detail can be considered in these steps, but the highlighted points are most important. At first, conducting interviews for gathering a training set. So the output of the interviews should be labeled cases, which can be used to compute the most relevant words for each label in the second step. With this distribution, we can classify other case histories and assign the labels for the not annotated cases. So in the end, we can apply the process mining to generate a process model depicting the handled contents during the client cases. That's the whole plan at the end. So the first step is conducting interviews. So let's delve into it. How have we done it in the case study? So in our case study, we manually annotated the case histories with the respective caseworkers. So we had history, segmented it into 2-week time windows. And for each segment, we asked about critical incidents or critical events that occurred during these cases. These critical events were condensed into labels, and the labels you can see here. It's rather representative for the social service sector, but it's a good step forward with it. For each label, a list of representative words were computed using LDA. So for example, at residing situation, a word like kitchen is a relevant word because there was some problems with the kitchen, or they should have bought new furniture, something like that. So talking about text data, many words don't have a semantically high meaning regarding to the content, so it's advisable to pre-process the data and filter the text. But more important, so after pre-processing, the conducted interviews gave around about 170 documents as a training data, and the word distributions for every label. Some words are more important from these 3,800 words are more important for specific labels or less important for specific labels. And the next step is automatically labeling the other 2,000 case histories. So we conduct a classification task using the learned word distributions. So you see in the figure below how this works. So at the left, they are the learned distributions with the most relevant words. In the middle is the text to be labeled. Words which occur in the text and at the same time they are relevant for a label. They are highlighted here and they will be counted. So police is a word that is can be assigned to delicts or violence issues. And if enough words of a label can be found in the text, the label can be assigned to the text. So in this example, we see the delicts are have the most proportions of relevant words in there. So we can do this with a threshold. If the threshold is exceeded, we can assign the topic to the new document. It's possible to assign more topics to a document. So after labeling all the documents from the different cases, we generate an event log and use the labels as events. And then we can start the process discovery. And at the end of the process discovery, there is model. So this is a dependency graph. We use the process mining toolkit and the interactive data aware heuristic miner for that. On the edges, we can see the dependencies between the topics. Top and bottom are the start and the endpoints. So we can see somewhat the process here. This model itself was evaluated by domain experts through another interview, and they stated half of the model is correct, especially the relation between the topic relationships, residing situation, and financials is a good depiction of the reality, they said. Unfortunately, what you can see in this model, there are really meaningful connections to have rather low dependencies. So between relationships and residing situation, there's 0.24 dependency, whereas between residing situation to itself, it's almost 1.0. So, and the dependencies between the same topics are not that meaningful. So we have a bit of bias if you look at this model to see the relationships are not that much in the event log like it's depicted here. While the expert says said the usefulness is rather low, we had an interesting observation with the topic of supervision agreements. This topic contained problems with third-party caregivers. The experts doubted the truth of this statement, but if the model would depict it right, they said they have to communicate with other caregivers more. So we can derive possible action from this model already, even it's not stated as completely correct. So there are much more possibilities to interpret here, but going on, like I said, we had an evaluation to assess three things: the classification results, the accuracy of the word distributions, and the model by itself. So in the left table, you see the how well did the classifier perform. The classification matrix could be computed after a second interview. And in this interview, our domain experts assessed the automatically labeled cases. So we see in the classification metrics, the results did not shine, but are okayish. It's a bit better than a coin flip, some would say, but it's certainly some potential here. We have some issues regarding the text pre-processing and the low training data, so we can improve it a bit at least. So the right table contains the perceived ratings by the domain experts, respectively the caseworkers. We see we have for each label we have some relevant words, and the experts could say is this relevant or not relevant for this label. We see more words were rated inappropriate than fitting. So that's mostly because of the pre-processing, or the LLDA didn't filter enough of the general words. So there are something like Mr. or Mrs. in the singular label word distributions. So, and that's not meaningful for the topic at all. The expert says furthermore that the model is completely understandable and halfway correct, but it's lacking regarding usefulness. So mostly because they cannot see any further actions for their daily work in this model. So that's a bit of a bummer, but we can say, and we can conclude it here, that the results are a bit disappointing, I guess, but there are more details to delve into for improving the results. So certainly it's improvable by a lot. Here's some of the improvements are listed. We do have the problem that we assigned, that we didn't assign the label directly. We took the critical events. So that could be a bit of an issue for the accuracy of the results. So more training data and test set would be in every for every time. Is it a good thing? More directed pre-processing. I said it already. The pre-processing techniques we used so far were somewhat simple, I guess. So that could be improved as well. So, and for a model itself, it's advisable to select the cases, split the event logs for bits of similar cases. So we can cluster and make more models, which could be more accurate, I guess. So, and another thing is the detection of parallelism for the process mining toolkit. So if we have multi-labeled documents and derive from that the event log, we have more topics at the same timestamp, and we cannot. The program did not detect it as a parallel event, more like a sequence of events, and that's not right. So multi-labeling is not an option for this model. So there are certain room for improvement, but to be considered is LLDA is based on probability distributions. So no absolute accuracy could be expected. It's a common thing for text analysis methods. So it's a bit of a bummer that the model's usefulness is rather questionable for the caseworkers. But as I have stated, you can gather some insights. Maybe leaders may find it more useful, but the insights overall are a bit weak. So nevertheless, I would say it's a success. Without the topic modeling, and especially in our case study, the enterprise would have 4 activities or topics to distinguish from. So it's especially for this domain, considering the topic modeling and structuring the text beforehand is very fruitful. So in this case, the topic modeling enables the process mining. And that is the last word. Thank you very much for your attention.
Thank you for your great presentation. It's been very very interesting indeed. I know I have at least signed, I don't know, I'd say a handful of questions already. It's a very interesting topic anyway. So I'd like to see first, however, if there are questions from the audience, because they're always the most welcome interventions indeed. Again, Hamala Edwin. So he said, sorry, from the audience, Hamala asks us, I'm not familiar with this topic, but it sounds a lot like tags, or about the process of tagging in software. Are they similar? So
yeah, labeling and tagging, you could use it as synonymous, yeah. But the labels here, yeah, they should depict they should be a representative of the content. So the tagging is more for searching and structuring. But I guess it's most of it is the same, yeah.
Right. So any further questions from the audience? Let's see. Well, while they they warm up their fingers to type down the questions on the Q&A or to raise the hand for asking questions, I'd have some in the meantime. Right. So first, well, it's a very nice, challenge that the one you tackled in general, because actually extracting process knowledge from documents is kind of a hot topic, especially now. So, but actually over the last decade, I'd say, so very nice that the intuition you had about using topic modeling for documents. What I wanted to ask is, well, how about repetitions, right? So you were showing at slide 9, I think, a model with which was retrieved from the automatic extraction from models, I imagine. And then we saw, yeah, right, some, very recurrent repetitions. Could it be that perhaps it was due to the fact that certain words were repeated oftentimes within maybe closed documents within the documents, but not because they were representing an actual repetition of a task, but rather an explanation, a further explanation of what was meant before. Just, only you saw the data. I mean, I didn't had a look at the data yet, so you might know best. So could it be an explanation for it?
I don't get what you're referring to. You mean why it's the looping between the topics? You mean that?
Yeah, right. So I was wondering if it's because perhaps certain terms, key terms, are repeated oftentimes along the document, and therefore they consider as if the task is repeated over and over. Instead, it's maybe an explanation of what was said before, or something like that.
Yeah, we have to say it's a bit of the training data itself. Also the enterprise where we conducted our case study focuses itself on residing situations. So the other topics are not that much in the data. Nevertheless, the single, yeah, how to say it, the words are used for the, yeah, there are many general words in there, and if you have the most training data for the residing situation, the probability is high to get more of them at the further case history. But the problem is the vocabulary of the single persons. So they work on the same case and have the same vocabulary. And LLDA sees, okay, he uses the word kitchen very often, so it's residing situations, for example. So that could be an explanation. There's many issues with the text data by itself, so it's not reviewed, and there are abbreviations that no one understands, and sometimes sometimes other people or other employees write the reports. There's some of issues in the text data, so they have to be more reviewed for more accurate result.
Yeah, right. Yeah, I was smiling when you said about the the plethora of acronyms and abbreviations of all sorts that nobody could understand except the ones you said they pronounced them.
Yeah, right.
Because there were some in general you can see that in studies that involve like open source software or even email messages. In there you can see that there are certain things that only the writers understand, or maybe the recipient, maybe. So yeah, right. It's very interesting. I have just two questions, maybe for for the future work, perhaps. Of course, if you want to take it into account. One was, did the domain expert also suggest certain modifications to this very model, or could you retrieve some of the suggestions as a sort of reinforcement learning, so just giving some more indications to the engine so as to create something which is closer to the model that was expected? Or are you considering this as a possible avenue for future work?
So they stated they had some statements how to make the model better, but in the past we have learned that manually modeling is a bit of a hassle with the social workers. And for improving the model, the problem was they stated, even if I see the shortcomings of our process, we can't do much about it. So that's a bit of the problem. So for the improvement of the model, they said supervision agreements should be at the end. But that's not what the data said. And maybe it's a better for insights to let data speak, so you can improve your work. But nevertheless, the data are not that clean and the model is not that representative if you evaluate it that way. If that answers the question a bit, I hope.
Totally. Yeah, right. Yeah, of course. And right, so as long as I don't see any further questions from the audience, well, okay, I'll take the last bit of your patience to ask another question, which is in
Please.
this case, right. Especially in the information systems community, sometimes it happens that there are some live observations of workers in the field, and so there's someone taking notes of what they're doing at the moment, and they create a sort of log, in essence. Of course, it's again something which is not very accurate, but kind of testifies what's going on there. I was wondering, because if I remember correctly, one of the remarks from the domain experts was that maybe they didn't know exactly how to make use of this very valuable model. I was wondering if it was possible for you or your team, the project team, to go and maybe see how the processes or the services actually are enacted, and see whether actually this model complies with what is being done, and if not, where it doesn't. So in this case, it would be something like checking the conformance of this model with, which is extracted from from natural language text, with experience on the field, so to see what's going on there. Just wondering.
Yeah, that's a shadowing task, I would say, to be with the social workers and look at them while they are talking and doing the stuff with the clients. Or is that what you meant?
Yeah, right. If it's not possible at all, then it's a story, of course.
No,
well, just wondering if
it is certainly possible, but especially at interdisciplinary things, and they have a high occurrence of emergencies. So you can't be there for, don't know, they work at Sunday as well, and it's a bit, you can't log everything they did, and it's a bit it's a high effort, I would say. It's not necessarily the wrong direction. But what I see is in this model, this is not it's not refined enough to compared to the actual process.
All right. Sure. Great observation indeed. Thank you. Just out of curiosity. So let's see if there are any further questions. I think not yet, at least. Well, in case, there is always time to, gather together even virtually and, ask questions and mutual observations on what was being discussed. I thank again Felix for this lovely talk that concluded our trotting of the word from East to the Central Europe. It's been fun. Of course, none of this would have been even remotely imaginable if it wasn't for the incredible efforts of the organization. Thanks a lot, Laura, and all at the University of Melbourne for this great work. So coming up next, we would have for today in the Kaiser framework, the keynote speech and conclusion of the mobile workshop, whereas for BPMDS, we might see each other tomorrow morning, European morning, at 9:30 a.m. Central European time. Please translate into your local time zone if you like, with the joint industry keynote for BPMDS and MSAD, and then the session 3 from BPMDS would start at 11:30 Central European time. So thank you all for being here. It's been a great pleasure to be part of this session. Great. Thank you, and see you very soon. Bye-bye.
Thank you.
Thank you. Goodbye.